Okay, and the other issue we're going to tackle in this section now is how to take the derivative of logarithmic functions. And so that's what we're going to start with. So, and it's also going to be a chain rule that comes to our rescue here. So we'll start by letting a be a positive number that's not equal to 1. Really, and again, if you remember when we talked about logs in section 1.4, really the purpose of letting a be a positive number that's not equal to 1, we're just setting it up so that it's an appropriate base for a logarithm. And then we're going to define the function f by f of x is equal to log base a of x. And then this is the function that we really want to differentiate, right? That's what this is coming down to. So how are we going to find f prime of x? That's our challenge. And the way we're going to start is we're going to make an observation. So what happens if you take a, this base, and raise it to the power of f of x? Well, f of x is equal to log base a of x. So let's write that out. Let's write this as a to the power of log base a of x. And then what should be apparent here is that this is exactly what you see with one of the cancellation properties of logarithms. The a in the base and then the log base a in the exponent, they cancel out and they just leave you with just x. Okay, and really the point here, let's just summarize. The point is that if I take a and I raise it to the power of f of x, I end up just getting x, right? That's going to turn out to be really useful. So the way you should interpret this, and actually let me add a little bit more onto here. This is going to be true, for what values of x is this going to be true? This is going to be true for any positive number x. Right? Because we need x to be positive so that it makes sense to plug into the log for this statement to actually make sense, really, so that it's even in the domain of the original function f. So that's got to be true in the background. But this is true for every positive value of x. Therefore, this equation holds for every or any positive value x as well. Okay, so what that means is the identity function x and a raised to the power of f of x. So this is really the composition of the exponential function with base a along with the logarithmic function with base a over here. That's really what you have on the left-hand side. And this equation is saying that those are the same function if you restrict their domain to positive numbers. Well, if they're the same function, then their derivatives ought to be the same. Right? So that's actually a key fact here. If their derivatives are the same, well, what does that mean? Well, what's the derivative of the left-hand side? We could actually write it down, right? If we just take f to be the inside function, right, and we can use it to, and I mean, we're strictly looking at the left-hand side here, so just look at the a to the power of f of x. So now if I treat f of x like the inside function, I can use this rule to take the derivative of the outside function. I'll just have to make sure I also use the chain rule and take that into account and multiply by the derivative of the inside function afterwards. So what's that going to look like? And again, all of this is taking place on the left-hand side of the equation. We haven't even looked at the right-hand side yet. So, well, if I use the formula I just showed you to differentiate the outside function, I'll get a to the power of f of x times the natural log of a. And I'm just going to draw the bubble again around the inside function f of x. So that's the derivative of the outside function with the inside function left alone. But now I need to multiply by the derivative of the inside function. And the derivative of the inside function, well, we don't know that, right? F log base a, in fact, that's the rule we're trying to determine here. So we don't currently actually know exactly how to write down the derivative of f of x when in the sense of actually differentiating log base a of x. But what we can do is just use the notation. We can just write it down symbolically as f prime of x. There, we're not liars if we do that, right? Certainly we don't know what this is yet, but we can certainly still write it down. So that's the left-hand side. If I take the derivative, right? Let me rephrase. This is the derivative of the left-hand side of the preceding equation with respect to x. So the idea is that ought to be equal to whatever the derivative of the right-hand side of the equation is with respect to x. Well, what is the derivative of x with respect to x? Well, that's x is just x to the 1, so you can use the power rule, and you're going to get 1. So that is what we get if we take the derivative of both sides of the equation. And now let's also make use of the fact, well, a to the power of f of x, that's really just equal to x, right? So let's take advantage, or I guess I could be pointing to it right here. A to the f of x is just equal to x. Let's take advantage of that, plug that in here, and really, so in other words, this is just equal to x. So what you end up with is x times the natural log of a times f prime of x is equal to 1. And actually, what if we just solved this equation for f prime of x? That we'd be done, because look what happens if we do that. If we solve this for f prime of x, well, just divide both sides of the equation by x times the natural log of a. Just divide both sides of the equation by this, and you're going to get 1 over x times the natural log of a. So it almost feels like we cheated here because we never actually tackled log base a of x directly. We really just worked with the cancellation property over here. That came from this work up top. But nonetheless, here we now have a rule for f prime of x. It's just 1 over x times the natural log of a. So let's summarize that in a rule. Now that's our rule for taking the derivative of logarithmic functions. And we'll write it in operator notation. So the derivative with respect to x of log base a of x is just equal to 1 over x times the natural log of a. And that's true for any constant a that's greater than 0, but also not equal to 1. Like that's the requirement on a. Now in particular, this comes up often enough that we should ask this question: what about in the case when a is equal to the exponential constant e? So, well, let's put that special case down below. We'll handle that as a separate case. So in particular, the derivative of log base e of x, well, what's log base e of x? It's just natural log. That's what you'd write in that case, right? So this is really the special case when a is equal to the exponential constant e. Log base e of x is just natural log of x. Well, what would the right-hand side be? We'd have 1 over x times the natural log of e, and the natural log of e is just 1. So you'd just get 1 over x in that case. So that's your rule for the natural log. It's a little bit nicer. You don't have as much to worry about. But in general, if you're dealing with a log of any other base, then this is your rule. Okay, so that's how we can handle the derivatives of logarithmic functions. Let's look at some examples. So we want to differentiate the following functions. So let's start with the first one. So we got y is log base 4 of x. Well, that's just going to come straight from the formula. That's literally what you have here, except a is equal to 4, right? So we can just use this formula to instantly answer the question. Derivative of log base 4 of x is going to be 1 over x times the natural log of 4. So we can just write that down directly. So y prime is just 1 over x times the natural log of 4. So not much to that one. What about part B? We've got f of x is equal to the natural log of x. Well, just like part A, we can answer that directly using a formula. That's using this rule up here, right? That if you want the derivative of natural log of x, it's just 1 over x. So we can do part B instantaneously. Just f prime of x is 1 over x. So nothing mystical for those two examples. We didn't have to do any real deep work. But what about part C? Now we've got g of x is equal to the natural log of x cubed plus 1. Let's look at that one carefully. Well, you have an inside function here again. This is one of those cases where you have an outside function as the natural log, and the inside function is x cubed plus 1. So we've got an inside function and an outside function. We're going to need to use the chain rule. So I will now make a point of no longer writing these bubbles that I keep drawing. Whenever we're doing a chain rule, I draw these green bubbles around the inside function. It's time to maybe stop doing that, and I'll do that. I'll start with this example. We'll just write, we can still, it's not going to change how we handle it, but I just won't draw that anymore. But of course, the inside function is x cubed plus 1. And if you'd like to go ahead and draw that bubble, then go ahead and do it. But if you're wondering why I don't do them anymore, it's just because I've chosen to not do them from here on in. But it's wrong to do so. Okay, so but what are we going to do? We're going to differentiate the outside function first and leave the inside function alone. So it's natural log of the inside function. What would you do if it was just natural log of x? Well, you would use this rule to differentiate the natural log of x, right? It would just be 1 over x. So we're going to start by just going 1 over whatever's inside when we write down our derivative g prime of x. So we're going to go 1 over x cubed plus 1. So that's the derivative of the outside function with the inside function left alone. Right? We're just using this rule, right? It's derivative of natural log of x cubed plus 1. We have 1 over x cubed plus 1. But we're not quite done. We still have to also multiply by the derivative of the inside function, right? We have to multiply by the derivative of x cubed plus 1. And that's the only change we have to make, and that's essentially it now. We just need to work out what this smaller derivative is. And it's a polynomial, so we can use the power rule on each term as normal. So we're going to get, this will be 3x squared, because the 1 is just going to disappear when you take its derivative. So it's 1 over x cubed plus 1 multiplied by 3x squared. Really, that's just going to be 3x squared over x cubed plus 1. And that is your derivative for part C. All right, so let's do these other two. Now there's 2 left. For part D, we've got y is equal to log base 2 of x squared minus 5. So the outside function is log base 2, and the inside function is x squared minus 5. Let's use Leibniz notation for the derivative here just to be different. Again, you could write y prime if you like, but I'm going to write dy dx. Okay, so take the derivative of log base 2 of x squared minus 5. Start by just looking, okay, x squared minus 5, that's just an inside function. Worry about that later. Look on the outside first. We've got log base 2 of the inside function. So go up to the rule that tells you how to handle log base 2. If you have log base 2 of x, you would just go 1 over x times the natural log of 2. So what we're going to start with here is we're just going to go 1 over the inside function times the natural log of 2. So we'll start by going 1 over x squared minus 5 times the natural log of 2. But then, so that's the derivative of the outside function, where we left the inside function alone. But now, we're going to multiply by the derivative of the inside function, which is x squared minus 5. Okay, so take the derivative of this part after, derivative of x squared minus 5, you're just going to get 2x, right? Doing term by term. The 5 disappears, x squared becomes 2x when you take its derivative. So we got 1 over x squared minus 5 times the natural log of 2 multiplied by 2x. Let's just write this as, I can even fit it in here. We can just write this as 2x over x squared minus 5 times the natural log of 2. And that is our answer in this case. All right, so let's do the last one. We've got f of t is given by the natural log of sine of t. So again, we have a chain rule problem here. The outside function is the natural log, and the inside function is sine. So let's do the chain rule here. So our f prime of t, we're going to start by differentiating the outside function, but leaving the inside function alone, right? So we've got natural log of something. So what would you do if it was just natural log of x? Well, you would take the derivative of natural log of x and get 1 over x. So in this case, we're going to start with just writing 1 over sine of t. Right? So we've differentiated the outside function, natural log, but we left the inside function alone. And of course, now we have to multiply by the derivative of the inside function. So multiply by the derivative of sine of x, or not sine of x, sine of t. Okay, well, derivative of sine is cosine. So really what we have here is cos of t over sine of t. And well, you can stop there, or you can take the initiative to actually notice that that's actually cotan of t. So you can make it a little bit abbreviated by just using the fact that this is literally the definition of cotan, but it's fine to leave it as cos of t. Oops, I slid off the screen there. So I wrote the next step as cotan of t. You can leave it like this, cos of t over sine of t. There's absolutely nothing wrong with that, but that is, by definition, that's just cotan of t. So I'm going to write cotan of t. And that is how you can handle these examples. So the best thing to do is to just get some practice, and as usual, you can find plenty of exercises in the section 3.5 list.